All right, so derivative of a composite function. If y equals f of v and v equals g of x, in your book they use the dummy variable u. I chose not to. So if y equals f of v and v equals g of x, then the derivative of y with respect to x is the derivative of y with respect to v first times the derivative of v with respect to x. So in my example, like y equals sine of 2x, it's basically the outer function's derivative times the inner function's derivative. So the derivative of sine, using 2x as a variable. 2x is still in there as its variable. So when you take the derivative of sine, you get cosine of 2x. And then times derivative of 2x, which is just 2. And that's it. That's what this is saying. And this chain can go on. Okay. So here's one. This is a chain rule one. What we want to be able to do is see this as something to the 7th power. Something to the 7th power, you would apply which of the rules that we've done so far? 13 rules. Do you recognize it? Something to the 7th you would use power rule on. So you treat this whole polynomial as its own variable. Now you can substitute in. You could replace that with u if you'd like to, or v, or any other dummy variable. But I think it's better because as soon as you get beyond a chain of 2, the substitutions are really a pain in the rear. Like they make it more confusing, to be honest with you. But if you can see this, and I think a lot of you guys can, like your algebra, I think you guys are seeing this in certain forms, certain distinct forms of algebra. This is something to the 7th. So what do you think the derivative y prime of this guy might be according to the chain rule up above? So first thing we're going to do is apply the power rule, right? So bring the 7 out in front. This thing in parentheses is just a thing, it's its own variable. And then to the 6th power, so we have this so far. And then we just have to do d dx of this guy, x to the 5th minus 4x plus 8, and that's it. So we take the derivative of the outer function using the power rule. That's the dy dv part right here, and then times dv dx. Okay, if I were to call this v. What's the derivative of this part right here? So the derivative of this guy would be 5x to the 4th minus 4. And that's it. So in terms of this up here, if I were to call, say I call v, to show you a substitution just one time here, and then we're going to kind of get away from it. So there's v. So we would think of this as y equals v to the 7th. So when I say take dy dv, dy dv is the 7v to the 6th. That's the dy dv part of the chain rule. And then times dv dx is just taking this guy and doing the derivative of that. So derivative of that, dv dx would be 5x to the 4th minus 4. There's the dv dx is this guy, dy dx is that guy, and then how do we get to this matching answer? Plug it back in, plug what we labeled v back in. So if you can skip that substitution step, we'll make it better, I promise, when we get to beyond chains of 2. You don't want to do the substitution. All right. And just leave it like this. All right, here's our sine of 2x. So find dy dx if y equals sine of 2x. So dy dx equals the derivative of the outer function, which is sine. So we've got a derivative of the outer function. So derivative of sine of 2x would be cosine of 2x times the derivative of the inner function, yeah. It's 2. And so we have 2 cosine of 2x. And in the textbook, they make some generalizations about this. Anytime you have a trig function that you're taking the derivative of, and there's a scalar multiple in front of the variable, that scalar multiple is going to come out. The reason it comes out is the chain rule. You've got to take the derivative of this function inside of the trig function. All right. So now I just opened up a whole new world of functions that we can take the derivative of. All those ones that we looked at with the product rule and quotient rule that were squared, we could handle these that way as well. Rather than squaring it and then using the power rule on each part. Alright, so we've got f prime of x. We're going to find f prime of x if f of x equals 3x squared plus 1 squared. So you guys could have handled this before a couple different ways, but according to the chain rule, what's my outer function's derivative going to be? Give me the derivative of the outer. 2 goes in front of the whole thing. Treat that thing as your variable, and then it's to the first here, and then times. What is it? Yeah, that's it. I think it's pretty intuitive. Does it feel somewhat intuitive? I think so. The key is seeing it, and that's what you're going to be working on today. As you're working through the bookwork, you're going to run into problems where you won't, like, without your study buddies that are with you, you might not see the chain rule in there. Like, you might miss one of the chains. You'll see what I mean when you try it. So as you go through these, you need to check with each other. And that'll help you out. And you got to be really good at the chain rule before you do implicit differentiation. What's that? Implicit, I-M-P-L-I. Yeah, implicit differentiation just means applying the derivative to each term on both sides of the equation, even if the x's and y's are all mixed up. In other words, explicit differentiation would be I get it y equals, like all these, and then I just apply the rule. Implicit would mean it's not necessarily in y equals form, it's just in, just an equation with x's and y's in it. So remember all those conic sections we did? So you can actually implicitly differentiate all those relations, those conic sections and stuff. Yeah. It's a way to take an implicit relation and find the derivative of it. All right. So go ahead and write this one down. We're going to find f prime if f of x equals tangent cubed plus 4x. No, I'm getting cold now. That thing's blunt. Is it cooling off?
Yeah, it's cool. It's
I wore shorts today. One of my daughters has soccer practice today at Markham, and my other two come and we play tennis. It's quite an adventure. Not too young, but and then the other thing was Mr. Sarge wore shorts yesterday. He was really cold, so I had to at least not. Although today's warmer, so. Man, Mr. Sarge shows up. I thought it was cold yesterday. Mr. Sarge, he lives down the hill. I had it up the hill, so I could go to that. So I had to at least as tough as Mr. Sarge. Hopefully. Mr. Sarge, if you're out there, we're recording. All right. All right, so we've got actually a chain of 3 here. I'm going to rewrite this, so hopefully this will help you. So you got to be able to see this as a chain of 3. So here's how we'll rewrite it. Think of this as tangent of 4x. Okay, so right there is a chain of 2, right? So you got to take the derivative of tangent and the derivative of 4x. But then I put the cubed back on here. Now I've got a chain of 3. Yeah. So it's like you have a power rule here where tangent of 4x is your variable. And then you have derivative of tangent with 4x as the variable, and then derivative of 4x. So this is a chain of 3. Okay, and these are pretty common. If I had asked you to find, I had to be careful on that last test. If I had asked you to find like the second derivative of, say, I don't know, if it were like second derivative of tangent of 4x, right? You'd end up with a chain of 3 on that second derivative. Because derivative of tangent is secant squared. If it's secant squared of 4x, now you're in the same boat as this. So you got to be able to pick those out. So any trig function to a higher power than 1 with an argument other than just x is a chain of 3. Okay. So what do you think here? Give myself a little more room. F prime of x equals. So by the power rule, we've got 3 squared. So there's that, right? And then what next? Yeah, so derivative tangent is secant squared of 4x. You got other 4x in there still. And then times the derivative of the innermost function. Yeah, and the derivative of 4x is, so there it is. Yeah, and so these will be on the AP exam. They will ask you to do chain rule problems by the chain of 3. Probably a problem very similar to this. Okay, I would pretty much bet on it. And then it's gonna be in the multiple choice because this is skill based, right? So they're gonna have it written where they'll multiply the 4 and the 3. Just be aware of that. You'll figure it out. So, what's that? Yeah, it would be a 12 inside. I don't think they mess with any other. Oh, the other thing they might do is move this slide just squared through. So they might have something like this. Squared 4x secant squared 4x. This is totally fair game. What's that?
Would you have to also square the 4x? Or no, that wouldn't.
No, you wouldn't. No. So, but that's how it'd be written. Okay, on a multiple choice. Does that make sense? Yeah. Is that all right? Okay. So, moving right along here.
That's amazing.
Yeah.
All right. So do you think you could find the derivative of this guy? We've got f of x equals cubed root. Not that bad, my goodness. So cubed root of 1 plus 4x. Cubed root of 1 plus 4x. We can do one rewrite that I think might help you. Yeah, and that's really what you want to be doing in calculus, is you want to be thinking in terms of not roots and radicals, but rational powers. You really want to be thinking in that way. So we got f of x equals 1 plus 4x to the 1/3 power. Okay, now we can handle it. So f prime of x equals, here we go. What's the first part? To what power? Okay, good. Negative 2/3. And then times 4. That's it. And it would be written 4/3, and then they might. So just so you know, it might be written like this: fraction bar, 4 up here, 3 down here. You'd move this down. It'd be cubed root of 1 plus 4x quantity squared. Okay, the negative power, you move it to the bottom. This 3 is not on that 3. That's a cubed root. Cubed root. Remember, it's the root and then the thing in parentheses to the power. So the root is always the bottom of the fraction on these rational powers. So it'd be cubed root of 1 plus 4x squared. That's how I meant, right? In terms of if you're just, as you're going through the worksheet, just leave it at this point here. You'll see why. When you get Monday's worksheet, you'll really see why. You don't want to mess with simplifying it. But
So
just leave it.
we shouldn't do a lot on expected.
You don't need to. I'm just saying if you're doing multiple choice, which you will, when you practice a multiple choice, it'll be simplified. Even on the little computer practice ones I give you when we get to that stage. And then, of course, on the exam. What's that? Yeah. They don't get too crazy with it though on the exam. That's not bad. It's not bad. It's not bad. But it's the practice problems in the book and then on the worksheet give you a kid. So find f. This is f composed with g prime when x equals 0, and then we're given f of v equals 2v over v squared plus 1, and v equals g of x, which equals 10x squared plus x plus 1. So go ahead and write that down. Why don't you write that down? I think you'll probably want to have this example in here because you're going to have one like this in the textbook problems. And we should talk about different ways to approach this because there's more than one way. See what makes sense to you. Give a hint here. No wait on this. So any ideas, of one way you could do it? You could replace all those v's with that g of x thing. You mean? Yeah, you could. That would work. Yeah, that'd be fine. That'd be okay. Can you think of any? So that would work. That totally work. And you find the derivative, right? Doing whatever techniques you need to do, whatever rules you need to, and then you would eventually plug in 0. Another way to think about it is you really have a chain rule here, right? Chain rule, and the chain rule says the derivative of the composition of these two functions will be the derivative of the outer function, which is reflected by the 2v over v squared plus 1, times the derivative of the inner function, which is just the g of x function. You can just multiply those two together. Now they aren't in the same variable, right? But that's not a problem. We just take the derivative of the thing in v and then substitute. And then plug in 0. But my hint here is you can think of this as f prime of g of 0, g prime of 0. That's what this is. Yeah. So it's f prime of g of 0, g prime of 0. So can you tell me here, let me move it, I don't want to move up too much here. So first of all, what's f prime here? What's f prime going to be? Quotient rule, yeah. So with the quotient rule, what do we get for f prime?
V squared plus 1 times.
Okay, so v squared plus 1 times 2 minus 2v times 2v, or 2v is 4v squared, all over v squared plus 1 squared, and then times g prime is just, we're talking about g prime of x right now. We're not putting 0 in yet. The g prime is 20x plus 1. And then if I want to put 0 in, what am I actually plugging 0 in for? Not quite. Just x, right? So I can put 0 in here. I can put 0 in there for x. I can't put 0 in for these v's though, but what could I put in for? Yes. So I go up here and I calculate g of 0, and g of 0 is 1. You see why? So g of 0, I got 10. So g of 0 is 1. So go back over here. We're thinking this is f prime of g of 0, g prime of 0. There's the g prime of 0 part. F prime of g of 0, so g of 0 is 1, so I just put a 1 in everywhere you see a v. 2, 1 squared plus 4 minus 4, 1 squared all over squared plus 1 squared. So there it is. And then you just evaluate it. And you could do that as separate like processes if that's easier for you. Like you could find f prime of g of 0, get that number. That's essentially what we're doing here. And then get g prime of 0 is super easy to get, and then multiply them together. And you avoid the potential mess of putting the thing with x's, the g of x, back in here with the 0 in there. You don't want to do that. That is basically what we're doing. So what do we get here? Why don't you guys go ahead and do the arithmetic? We'll see if we get at least 3 of us with the same value. Yeah.
Why can't you basically take f of g of 0 and then take the derivative of that?
F of g of 0.
I guess that's exactly what you did. I was thinking of it. I love it. Yeah, I love it. I think I got there.
So what do you guys get here? This is all conjugate. So 1 plus 1 is 2, that's 4, minus 4 is 0. We end up with 0 here times 1, which is 0. How's that work? And it amounts to nothing. That's what it means. Cute. Probably won't. Yeah, this is probably the best example. That would be the wrong.
Right.
That's what we call wishful thinking. All right. That's like when my algebra students, as soon as I show them like any in equation solving or systems of equations, you know, the all real numbers or the no solution cases, like they want to say it on everyone. So instead of doing the word, they'll just say, oh, it must be one of those. But or if like it comes out and the x value is a fraction or a 0, they go, oh, it must be no solution. Instead of plugging in the fraction. Wishful thinking. All right. One application of this, and I think this is the last thing. So it says find the points. Find the points. Example 7. What do you think, weird guys? Sorry, that was wishful thinking. So find the points where the tangent line is horizontal. If y equals cosine of 2x plus 2 cosine of x on the closed interval 0 to 2 pi. So find the points, plural, where the tangent line is horizontal. This is the typical type of problem where they might ask it, and it could even be on a free response on the AP exam. It would be really easy to miss using the chain rule on it. So you need to make sure you use the chain rule. It's a subtle one. It's just in that first term, that's it. But If you don't use it, it really messes you up. So what's the first step on this? We're going to find points where the tangent line is horizontal. As soon as they say tangent line, we're thinking that all the time because we're in first semester. Calculus 1. Find the derivative. So y prime is equal to, what's the derivative of this guy? 2 sine 2x. You've got to have the 2x as the argument in there. You've got to have that 2 out in front, which is the derivative of, oh, negative x. Right. Negative 2 sine 2x minus 2 cosine of x. You know, really, we could use the chain rule on this. Not cosine, but sine. Talk and derive at the same time. So 2 sine of x. And really, guys, we're using the chain rule on this as well. The derivative of x is 1, so we've been using it all along. What's up?
So where did the 2 come from in front of the first sign?
In front of the first one?
Yeah.
By the chain rule. We've got to remember to take the derivative of the inner function.
Oh, you skipped that with the word. Okay.
Yeah, I did. So
Alright.
the work would be, you know, d dx of cosine of 2x. What we end up doing is taking the derivative of just cosine, which is negative sine of 2x, but I've still got to apply d dx to the 2x. That's what the chain rule says. And then what do I do with this to find out where the tangent lines are horizontal? So that equals 0. So we've got 0 equals negative 2 sine 2x minus 2 sine of x. And then our trig and algebra, you know, everything we did last year comes into play. How do I handle something like this? Any ideas? Okay, we're going to find all the solutions to this between 0 and 5. Now, if you're allowed to use your calculator, you know, just figure it out that way. You're going to get decimal values that really equate to exact values that are special angles on the circle. Probably you wouldn't be allowed to use your calculator. You should probably be asked to solve this. So any ideas on how to do it? They're different variables though, so you can't factor out a. Okay, I'm going to give you a hint. Add 2. You could, but then you're still kind of stuck because it's like you have sine of y in there and sine of x. It's like you have 2 different variables. This goes back to one of the identities you do need to know. Did you?
Oh, I don't know what it is, but I called it.
You called it? Okay, good. This one you do need to know. I'm going through in my mind making sure I know it because I'm saying it. I do. I'm remembering it now. This is a double angle for sine. What's the double angle for sine? Because somehow I have to get this, guys, I have to get this into the same variable as this. Otherwise, you're guessing checking your way. You could do that. It's only 0 to 2 pi. You could guess and check your way to the solution. But if we want to algebraically do this, I've got to rewrite this as negative 2. What does sine of 2x get replaced with? 2 sine of x, cosine of x. This is one of those that can pop up at any time as you go through calculus. You need to notice. A minus 2 sine of x. So here's what I have. It's in a polynomial sort of form here. So we've got 0 equals negative 4 sine x cosine of x minus 2 sine of x. Okay, now you can do what Jeremiah suggested. Factor out a sine of x. Factor out a GCF of sine of x. Can we get rid of this negative sign here? Yeah, we take that out. We could take out actually a negative 2 out, right? So got 0 equals negative 2 sine of x. So negative 2. We could totally divide out that negative 2 and get rid of it, but we've got negative 2 sine of x, and we're left with 2 cosine of x plus 1. Remember doing this last year? This was a tough one last year. You know, some of you, when you have that mixture of cosine and sine, you know, I tried some guess and check, I just couldn't figure out what it was. But yeah. Set each of the terms equal to 0 and solve that. So, and I can cancel this -2 out. That gets rid of that. So I've got over here either sine x equals 0 or 2 cosine x plus 1 equals 0. This one would amount to cosine of x equals -1/2. So I don't necessarily get it into inverse sine or inverse cosine. You're just thinking of all the places that have a radian measure that matches up with a sine value of 0, or a radian measure that matches up with a cosine value of -1/2. And we're only thinking through one cycle of the unit circle from 0 to 2 pi, is what it said on there. So I'm going to have how many different solutions? You know? Where does sine of x equals 0? Sine of pi over 2 would be 1. So 0 and pi. And where does cosine of x equal -1/2 on 1? Yeah. So it's at 2 pi over 3 and 4 pi over 3. So we've found all the values. I put a graph up here just in case we wanted to graph it. Do you have a picture in your mind of what this looks like, this original function? Can you draw it in the air? That's not terrible. Yeah, it's just this. So we're finding from 0 to 2 pi all the places where it has a tangent line that has a slope of 0, and it's also representative of all the what we call relative maxes and mins of this thing. So these are the x values where the thing either hits a high point or a low point as it's cycling. Okay, and there's 4 of them here. 1, 0 to 2 pi. Should we graph it? Let's graph it on the graphing calculator. It'll be better since we have it, and then we'll just verify that that's what we have. Cosine 2x plus 2 cosine x. Make sure you're in radian mode. We have cosine of 2x. What was the rest of it? Plus 2 cosine of x. How about we hit zoom Z trig number 7? Okay, so it's got some extra squiggles in it. So from 0 to 2 pi, we've got, see, where did we say the tangent line went horizontal? I think we said at 0, right? At 0, at 2 pi over 3, and then here again, and then here again. I don't know which that. So one of them is pi, and then 4 pi over 3. So it's, here they are. Let me show you. Let me show you here. Here's the, when x equals 0, you've got a tangent line that's horizontal. Here's when x equals, what do you think that one is? You have 2 pi over 3, pi, and 4 pi over 3. This is 2 pi over 3. Right here you got another one. And here you got another one. So this one is pi, and this one is 4 pi over 3. So there they are. All 4 of the places where that graph goes horizontal, or the tangent line to the graph goes horizontal from 0 to 2 pi. Okay. Does that conceptually make some sense? What's that? So I typed in this, and then I did it in Z trig. So in Z trig, I think each one of those hash marks is a, if we're going to graph it, I think they reach a pi. Or was it half pi? Okay, so pi over 2. So it went pi over 2, pi, 3 pi over 2, 2 pi. And I think it has one more hash mark beyond that, right? So it goes to 2.5 pi on the right. What's that?
I can get those.
That was from the original place.
Oh,
We were, okay, just to put this, so this graph right here was the original function, and we took the derivative in order to find all the x values on 0 to 2 pi where the tangent line went horizontal.
so actually this guy is showing what all the work.
Yeah.
Okay.
Well, it's showing, we can see now visually the 4 different values we got for x that correspond to a tangent line going horizontal. And those are also relative maxes and mins, we would call them. We're going to learn more about that in the next chapter. So that's it for now. Any questions on this before I have you practice it?
Sure.
Okay.